Hello, I am Mrs. Ruma Dhanwate from Aryan College of Arts, Commerce and Science, and in this video lecture we shall see the system structure. We shall see first the storage manager and query processor. A database system is partitioned into modules that deal with each of the responsibilities of the overall system. The functional components of database system can be broadly divided into the storage manager and the query processor components. The storage manager is important because databases require a large amount of storage space. In big organizations like corporates, the corporate database ranges from hundreds of gigabytes to lot of terabytes of data they have. That is, they have a large amount of databases which require large amount of storage space. Since the main memory of computer cannot store this much information, the information is stored on disk. Data are moved between the disk storage and main memory as and when needed. Since the movement of data to and from disk is slow relative to the speed of the central processing unit, it is necessary that the database system structure the data so as to minimize the need to move data between disk and main memory. Since the data is large in corporates and large organizations, it is not possible to save all the data at one place. So the data is stored on the disk. The query processor is important because it helps the database system to simplify and facilitate access to data. The query processor allows database users to obtain good performance while being able to work at the view level and not be burdened with understanding the physical level details of the implementation of the system. Storage Manager. The Storage Manager is the component of the database system that provides the interface between the low-level data stored in the database and application programs and queries submitted to the system. The Storage Manager translates the various DML. DML is the data manipulation language statements into low-level file system commands. The storage manager is responsible for storing, retrieving, and updating data in the database. Now the components of storage manager. The components of storage manager, the first is authorization and integrity manager, which tests for the satisfaction of integrity constraints and checks the authority of users to access data. Because there will be a large database and number of users who will be accessing the same database, it is required that you give an access as per the requirement of a particular user. So it tells you how and what data should be accessed by a particular user. Next is the transaction manager, which ensures that the database remains in a consistent, that is correct state despite system failures, and that concurrent transaction executions proceed without conflicting. File Manager, which manages the allocation of space on disk storage and the data structures used to represent information stored on disk. Buffer Manager is responsible for fetching data from disk storage into main memory and deciding what data to cache in main memory. Now, in the previous slides, we have seen that in the corporates, you will be having large number of database and which require a large space. And since all the data cannot be stored at one place, they are stored in the disk. Now, since they are stored in a disk, they have to be brought into the main memory for execution. So here comes the responsibility of the buffer manager, which fetches the data from the disk and keeps it in the main memory. The storage manager implements several data structures as part of the physical system implementation. Data files, data dictionary, and indices. Data files, which store the database itself. Data dictionary, which stores metadata about the structure of the database, in particular the schema of a database. And indices, which provide fast access to the data items. Next is the query processor. And the components of the query processor are DDL interpreter, DML compiler, and query evaluation engine. DDL interpreter. It interprets the DDL, that is data definition language statements, and records the definitions in the data dictionary. DML compiler, which translates DML statements in a query language into a evaluation plan consisting of low-level instructions that the query evaluation engine understands. That is, it converts the data manipulation language statements into the low-level instructions which is understood by the query evaluation engine. The DML compiler also performs query optimization. It means that it picks the lowest cost evaluation plan from among the alternatives. That is how quickly you can get the results. That is query optimization. Next is the query evaluation engine, which executes low-level instructions generated by the DML compiler. Next is the transaction management. The transaction manager consists of the concurrency control manager and the recovery manager. Now, often several operations on the database form a single logical unit of work. For example, money transaction or fund transfer in a bank account. The funds transfer must happen in its entirety or not at all. This all or none requirement is called atomicity. It is essential that the execution of the funds transfer preserve the consistency of the database. For example, some balance of two accounts must be preserved. This correctness requirement is called consistency. It means that, for example, you have two accounts, account A and account B. And in account A, you have 5,000 rupees, and in account B, you have 500 rupees. And you want to transfer the amount of 500 rupees to account B. So this should happen totally. That means in account A, what should remain? 4,500, and in account B, you should have 1,000 rupees. So if this transaction is correct, then it is called as atomicity. That means the whole transaction should happen properly. That means the amount from A should go into account B, and account A should have 4,500 and account B should have 1,000 rupees. So this is called as atomicity. And then you have consistency. Consistency says that the total amount of A and B should be the same before the transaction and after the transaction. So before the transaction, account A had 500 rupees, 5,000 rupees, and account B had 500 rupees. So the total amount of A and B was 5,500 rupees. When the 500 rupees from A was transferred to B, after that A had 4,500 rupees and B had 1,000 rupees. If you sum this, you will again get 5,500. So you have the same amount before and after the transaction. This is called as consistency. Next is durability. After the successful execution of the funds transfer, the new values of the balances of both accounts must persist despite the possibility of system failure. This persistence requirement is called durability. It means that after the transactions have been made in account A and B, if the system fails or some kind of failure happens, still the transaction which has been made should be there in the system despite the system failure. So this is called as durability. Next, a transaction is a collection of operations that performs a single logical function in a database application. Now it means that the whole transaction, which includes the subtracting of the amount from A and adding the amount to B, this whole thing at a time is called as a transaction. That is debiting the amount from A and crediting the amount to B. These two steps is called as a transaction. So a transaction is a collection of operations that performs a single logical function in a database application. Each transaction is a unit of both atomicity and consistency. Thus, we require that transactions do not violate any database consistency constraints. That is, if the database was consistent when the transaction started, the database must be consistent when the transaction successfully terminates. It is the programmer's responsibility to define properly the various transactions so that each preserves the consistency of the database. Ensuring the atomicity and durability properties is the responsibility of the database system itself, specifically of the recovery manager. In the absence of failures, all transactions complete successfully and atomicity is achieved easily. Because of various types of failure, a transaction may not always complete its execution successfully. Therefore, the database must be restored to a state in which it was before the transaction in question started execution. The database system must therefore perform failure recovery, that is, detect system failures and restore the database to the state that existed prior to the occurrence of the failure. When several transactions update the database concurrently, the consistency of data may no longer be preserved, even though each individual transaction is correct. It is the responsibility of the concurrency control manager to control the interaction among the concurrent transactions to ensure the consistency of the database. Now this is a system structure, and in this system structure you will see here you have naive users, application programmers, sophisticated users, and database administrators. That is, we have seen the types of users of a database management system. So these are the types of users and what they use or what they do. Naive users use the application interfaces. Programmers write the application programs. Sophisticated users, also called as analysts, use the query tools, and the database administrators use the administration tools. Now this part is a query processor which contains the application program's object code. You have a query evaluation engine, then compiler and linker. You have DML queries, DDL interpreter, DML compiler, and the organization. This is part is a storage manager which contains the buffer manager, file manager, authorization and integrity manager, and the transaction manager. And this is the disk storage where your data is stored, that is data, indices, data dictionary, and statistical data. So this is the system structure which contains the users, what they do, then the parts of the query processor, the storage manager, and the disk storage. Now we shall see the database architecture. The architecture of a database system is greatly influenced by the underlying computer system on which the database system runs. Database systems can be centralized or client server where one server machine execute work on behalf of multiple client machines. Database applications are usually partitioned into 2 or 3 parts. In a two-tier architecture, the application resides at the client machine where it invokes database system functionality at the server machine through query language statements. In a three-tier architecture, The client machine acts as merely a front end and does not contain any direct database calls. Instead, the client end communicates with an application server, usually through a forms interface. The application server in turn communicates with database system to access the data. So these are the diagrams of two-tier and three-tier architecture. Now this and this are the clients, and this is a server, and this is a server as well. Now in the two-tier architecture, the user interacts with the application, and application directly interacts with the database system on the server. Whereas in the three-tier architecture, the user interacts with the application, uh, then application client interacts with the application server, which in turns interacts with the database. Now this is the two-tier and three-tier architecture. Thank you.